For my study, I've decided to investigate whether step-over basins along the westmost section of the North Anatolian Fault Zone impact fault rupture propagation. The North Anatolian Fault Zone is a large-scale continental strike-slip fault system that extends 1,400 kilometers from the Karlovia Junction in the east to the Aegean Sea in the west. The westward extrusion of the Anatolian Plate accommodates for the northward collision of the Arabian Plate with Asia. This causes a primarily compressional regime in the east and an extensional regime in the west. It's accommodated by a slip rate of up to 24 millimeters per year. However, this is not equally distributed across the fault's length. In some areas, fault rupture propagation is restrained by fault stepovers, and that's what we'll be investigating today. Internal deformation from the counterclockwise rotation of the Anatolian fault block has caused destructive earthquakes to migrate over 1,000 kilometers throughout the 20th century. The spatial proximity and rapid succession of these earthquakes strongly imply an interaction between sequence nucleation events, but exactly how this is the case is unknown. My talk will primarily focus on the Izmit earthquake and how fault rupture propagation here has been limited by fault stepovers. The highlighted section shows the fault rupture profiles of the most recent earthquakes along the North Anatolian Fault Zone. As you can see, it mostly follows a linear profile, with exception to the two splays north and south of the Olmec Mountains. This figure shows the fault segments and connecting stepovers in greater detail. The Izmit earthquake ruptured the northern branch along four distinct structural segments. From east to west, these are the Karadir, Sakira, Sapancia, and Guluk fault segments. The length of these segments range from 26 to 36 kilometers, and they are bounded by right n-inch-long stepovers and gaps in the fault trace. In some cases, distinct structural basins have formed within these intervening stepovers, indicating that the segments may be long-lived despite the active nature of the fault. This already suggests that they may be able to negate rupture propagation as they have been stable throughout time. The Izmit earthquake nucleated within or near to the Guluk stepover and propagated bilaterally to the east and to the west. To the west, 4.5 meters of surface rupture and up to 7 meters of subsurface rupture was almost entirely arrested by the 4 to 5 kilometer wide Kara-Mürzil stepover. To the east, 3 to 4 meters of surface rupture and up to 4 meters of subsurface rupture propagated through the 2 kilometer wide Sapancia stepover. Fault rupture continued to propagate up until the Efton Lake stepover. However, the lack of propagation here could have been due to the surface displacement of only 1 to 1.5 meters, less than a third observed in the other three segments. And this is because it was more than 65 kilometers from the epicenter, and consequently, the fault rupture propagation wasn't as strong. We will now zone in more closely to two of these specific areas, namely the Kara-Mürzil and Sapancia basins. The top figure shows the 5 kilometer wide Kara-Mürzil basin separating the Yalova and Guluk segments. And detailed field mapping and paleoseismic trenching shows that the surface rupture did not occur across the Herceg Peninsula on the Yalova segment. An inversion of teleseismic data suggests a similar pattern is in place for subsurface rupture. However, radar interferometry and GPS data show that there was crustal strain of 1 to 1.5 meters. And while strain can be observed in the field, we cannot reconstruct a rock's deformation history, and consequently, we are unable to determine whether this strain was coseismic or postseismic. There is potential that the minor subsurface faulting was a sympathetic displacement, and if so, this would imply that the segment was stressed very close to the surface rupture threshold. But nonetheless, the Kara-Mürzil stepover basin arrested most of, if not all of, the subsurface and surface ruptures, implying coseismic rupture on the west end of the Guluk fault segment concluded here. The Sapantia segment, shown below, covers alluvial floodplains and bedrock ridges that follow a pre-existing fault trace, evidenced by side hill scarps, tonal lineaments, and linear drainages. To the east, bathymetric data shows the Sapantia segment forms a 1 to 2 kilometer wide, right-releasing step-over basin to the SARR segment. This step-over is occupied by Lake Sapantia. As you can see from this more detailed figure, the Sapantia Fault defines the northern margin of the basin, extending almost entirely across the lake, and this trace has been identified as a prominent scarp on the lake floor. All evidence suggests, however, that the SARR segment concludes at the east margin of the basin and is not expressed by the lake's bathymetry. Co-seismic rupture from the Izmit earthquake propagated through the Sapantia stepover, evidenced by right lateral slip of approximately 3 meters on both sides, and consequently we look for a reason why this occurred here and not at the Karamürsel basin. This theoretical model was produced by Lettis et al., and it attempts to constrain the impact of stepovers in arresting fault propagation. It supports all the data from the field observations, and it uses an elliptical slip distribution model, which was most accurate in recreating the spatial distribution of stress. In this case, it shows that where a propagating rupture increased the stress on the tip of an adjoining fault segment, this allowed the rupture to propagate across the intervening pull-apart basin or stepover. The figure on the left shows, on the right, shows a hypothetical scenario with a constant displacement of 5 meters along the entire Gulick fault segment. In other words, it represents an extreme case where part of the Gulick segment closest to the Yalova segment ruptured with the maximum observed displacement. Even in this extreme case, the Yalova segment was not subject to increased Coulomb stress and is in fact in a zone of reduced stress, which would help prevent slip. Consequently, the model supports the ability of the Karamürsel stepover to arrest fault propagation, implying any strain-related features on the Yalova segment were post-seismic. The model results for the Sapantia stepover, shown on the left, identify the slip on the Sapantia fault segment caused significant increase in Coulomb shear stress in proximity to the SARR segment, triggering it and allowing for continuation of rupture to the east. Stepover width has been identified as a more impactful constraint on fault propagation than area or length, and the ratio between stepover width in kilometers and strike slip displacement ranges from about 2.5 to 1 to 1 to 1 as displacement increases. As we can see from the y-intercept on this graph, a minimum stepover width of 2 kilometers is required to resist any fault rupture propagation. The line of best fit shows that when stepover width is beyond 4 to 5 kilometers, rupture is rarely able to occur, even when displacements of up to 6 to 8 meters are present. If accurate, these results provide important constraints on the probability of multi-segment ruptures. For example, where there is a right-releasing stepover with a 2 kilometers width, it should not be identified as a barrier to any fault rupture propagation. Secondary structures such as normal faults naturally provide a potential error in this, as there is an ability for secondary structures to further prevent fault rupture propagation by increasing the strength. However, it is clear that we conclude that fault stepover width is an extremely important constraint on fault rupture propagation. It's now been nearly 22 years since the last major earthquake, meaning elastic strain could be accumulating and the probability of a multiple segment rupture is increasing. In 1766, in the previous sequence, the fault ruptured through the Mara Sea and into the Gallipoli Peninsula. If this were to occur with the present sequence, there could be a multi-hazardous risk to the 15 million people that inhabit Istanbul. And consequently, it's extremely important to further understand the process of whether fault stepovers are able to prevent fault rupture propagation. Thank you very much for listening, and I welcome any questions.